Hello. Okay, so I want to do one other problem that's got to do with optimization. And it's something that's a little more complicated than the simple add the numbers up and you get this and you multiply the number, those same numbers and you get that. Something that applies to a problem that might be a practical purpose. And one that I found in the text that I'd used in the past was, and it's got a visual in there, so I want to use it in that direction. So if you could bear with me a second, I'm going to go over to the text and show the problem actually. All right, and here's the problem. I think you can see that. I hope you can. The focus looks pretty good. The problem is this. What are the dimensions of an aluminum can that holds 40 cubic inches of juice that uses the least material? Assume that the can is cylindrical and capped on both ends. All right, so there's a couple of pieces of information here. Optimization problem, we're trying to find, we want the can to hold 40 cubic inches of juice. We usually don't talk about cubic inches, do we? We got fluid ounces and that kind of stuff. But they're talking cubic inches and uses the least material. So there are two formulas that we're going to need. Again, you're going to have two formulas here. One of them you're given the value of, which is a constraint. And the other one, you're going to have to maximize or minimize, whatever the circumstance is. That's optimization. That's optimizing. So we end up with it holds 40 cubic inches of juice. That's got to do with volume. You're talking about space inside of a container. So that's volume. And then uses the least material. So in this case, we're talking about aluminum cans. So the can that uses the least aluminum. So you've got a situation of the outside of the label side of the can, and you got the top and the bottom, and those two added together. And so that's talking about surface area. So two formulas we're going to need are surface area and volume. So I'm going to take us over to the my iPad now and get onto the screen. We're going to work through this problem and come up with a solution. What are the dimensions that optimize that circumstance? Okay, so I made a quick little sketch here of the can on the left there. They're assuming it's a cylinder, and they mean right circular cylinder. Cylinders don't have to be round, they don't have to be the circular. And this situation, they're assuming it is a right circular cylinder, right meaning that it's straight up and down, and circular meaning that the base is a circle, all right? And as in other shapes, like if you had a box or something like that, the volume that you could calculate, is length times width times height. And length times width is actually finding the base, the area of the base of that box. Well, so the whole idea, if you've got a cylinder of any sort, then the volume is going to be the area of the base times the height. In a box, it's length times width times height. In a circular cylinder, it's going to be the area of the base is the area of the circle times the height. Let's go into this now. Again, the area of the circle is equal to pi r squared, right? So the volume is going to be equal to, the volume of that cylinder is going to be the area of the base times the height. So let's write that down as a formula here in forms of V. V equals pi r squared times the height. And you notice it's in terms, that function is in terms of r and h. Now, surface area. I don't know if you've ever seen this before. Some of you may have. But when you cut open a can, how do you find the surface area for that, for that, the amount of material you need to make that can? And what I want to point out is that if you cut the can down the front, okay, we slice it there, and then roll it out, just roll it out like this. There's no top and bottom on this. We're going to cut it and lay it flat over here as well. Whoops. Well, notice what that shape is going to be, okay, when you're done with it. So when you lay it flat, it's going to be a piece of metal that looks like that. Okay, and it looks like that when it's laid flat. So it's actually a rectangle. And what are the dimensions of that rectangle? Well, if we've got the cylinder we had was R radius, and the height was on the side here, and this is the R radius. Right? So what are the dimensions? Notice what that flat top side and top and bottom edge of that piece of metal are going to be. It came from the circle being laid flat. So that was actually the circumference of the circle. So it turns out then the circumference of the circle, if you remember, is equal to 2 pi r or pi d. 2r is sometimes referred to as the diameter, and twice the radius is the diameter, but 2 pi r is a formula I kind of grew up with. And so we've got the circumference is 2 pi r, and that is the length of this side, is 2 pi r. So what is the surface area of the shape? I'm going to abbreviate that down to SA. Really, we need one letter. I'm just going to call it S. Okay, S is not an ideal variable to me because it kind of can look like a 5. But if you notice, the surface area then is going to be equal to, you've got, well, first of all, it said you had the top and the bottom of the can. So that's pi r squared twice. So you got 2 of those, 2 pi r squared. And then you've got the labels, the outside of the can, laid flat. We got 2 pi r times h. So notice that that formula is in terms of r and h, just like this one is. So we need to pick one of the letters. Notice what we're doing. One of them we've been given the constraint of. We're told that the volume is 40 cubic inches. So we've got this one. 40 equals pi r squared times the height. The other one, we're trying to minimize the amount of material, which is the surface area. So that's the one we're going to take the derivative of. And therefore, we need to get it in terms of just one variable. R and H are the variables involved. And if you notice, R squared over here, we got an R squared over here. That means if you solve for R, you got to take the square root, messy number. Notice the H is standing there by itself in both equations. We got an H here and an H there. So if we can go back to the constraint equation, the one that's got that 40 on it, solve for H, substitute that back in, do the other one, it'll be the more straightforward solution, I think. And I think that's kind of obvious. So we're going to come back over here to the volume equation and solve for H. What do I need to do to get H by itself? I divide by pi r squared. All right, therefore H equals 40 over pi r squared. All right, so there's our H, and that is what we can substitute into the other equation now and get it in terms of just one variable, get it in terms of just R. We get rid of that H. So we end up with S now is equal to 2 pi r squared. The R is going to stay there. This R is going to stay also, but we're going to replace the H with 40 over pi r squared. And as a result, we can simplify that a little bit. So we end up with 2 pi r squared. Looks like the pi's cancel. One of the r's is going to cancel. That leaves us with 2 times 40 over r, which is equal to 80 over r. All right, so I'm going to rewrite that one more time. I'm going to write it as a function of s in terms of r now is equal to 2 pi r squared. And I'm going to write this in a form so we can take the derivative of it, move the r upstairs. That means the exponent becomes negative, plus 80, move the r up to the negative 1. All right, now that is a function we can take the derivative of, set it equal to 0, find the max, sign the max, the min, whatever the situation is we're finding, set it equal to 0, solve for r, and answer the question. What are the dimensions? That'll give us the r. Then once we get the r, we can plug that back over into this equation and figure out what h is. That's the goal of the problem, okay? So let's take the derivative next. First thing we're going to do, so we're going to find, not the first thing, we're going to do this right now. So we're going to take the derivative of s with respect to r. So I'm going to use the notation, start using the notation there, equals, so I'm derivative with respect to r. This is our x. R is our x. So that's the variable of concern. The 2 comes down front. I get 4 pi. We subtract 1 from the exponent. You've got 1. So it's 4 pi r. Plus, we've got, bring the negative down front, right? We get negative 80. That's I'll put the 80 out front. We got a negative 80. I'll make it a negative out front. There's a negative 80. And that subtract 1 from the exponent means that negative 1 goes to minus 2. And let's rewrite this now. We get 4 pi r minus 80. And the r is going to the denominator. The r squared is going to the denominator. There's our function. So the derivative is equal to 4 pi r minus 80 over r squared. Now, set that equal to 0, solve for r. So set it equal to 0. All right, so we've got a subtraction problem involved. So if we add the negative, we add to get rid of that negative sign, we'll get an equation and both sides will be positive. So we end up with 80 over r squared equals 4 pi r. Okay, we're trying to solve for r. So I need to get the r squareds out of the basement, move it up. So I got to multiply each side by r squared, right? So I end up with 80 equals 4 pi r. And again, let me write that out. I multiplied each side by r squared and end up with r to the third over on that side. And now simplifying, solving for r cubed, I divide each side by 4 pi. So I end up with r to the third equals 80 over 4 pi. And that simplifies down to 20 over pi. Therefore, solving for r, I need to take the cube root of each side. R then equals the cube root of 20 over pi. Do that on the calculator real quickly. And I end up with, I do 20 over pi. And 20 over divided by second, yeah, I get 6.36. And then I take the cube root of that. Now what I'm going to do, for simplicity's sake, I'm just going to raise this to the fractional exponent that cube root is indicating. So that, how do we write that? That's to the 1/3 power. 20 over pi to the 1/3. And so when I write this out on the calculator, I got to make it raise it to the power and raise it. I'm going to put in parentheses, because I'm not want to raise it to the first power and then divide by 3. I want to raise it to the 1 divided by 3 power. And that ends up giving me r equals 1.8533. And let's just round that to r is approximately 1.85. All right? 1.85 what? Part of the answer. It's talking about cubic inches, so therefore this is inches. All right, now, like I said before, we're going to plug this in now into the function we solved for h and figure out what h is. So h equals 40 over pi r squared, and we got 1.85, and I'm going to put, what I'm going to put in there, that's going to be, that squared. I'm going to go ahead and leave what's on my calculator right now, that whole thing. Instead of rounding it to 1.85 and get a rounded answer, I'm going to put the exact answer in there, the number that's out in the calculator, anyway, out to that many places. I'm going to square that number, like in the formula, square it, multiply times pi, and then take that answer, 40 divided by that, and it'll be the height. So I end up with 1.853, yada, 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 raised to the second. Got it, 3.43, yada. And multiply that times pi, 10.79, etc. And now I take 40 and divide it by that. Divided by second answer. And I got so h is equal to 3.7067. So I think that's a safe rounding is to the 10th place. Look at that. Equals 3.7. So the height equals 3.7 inches. That's what H is. So remember the answer, we used R to represent radius, and we used H to represent height. So a good answer would be that the radius is equal to approximately 1.85 inches, and the height of the can is equal to approximately 3.7 inches. All right, optimization problem where you've got two different equations. One is a constraint equation. The other is the number you're trying to optimize. You're trying to find the max, and in this case, we're trying to find the min. So there you go. Take a look at that. You look back through this and go back through and be able to work the problems I've given in Sapling section 4.7. Several are related to this type of thing, okay? Take care.